In the previous chapter, we looked at how atoms can bond together to form a molecule. Now we're going to take one step further to look at how a large number of molecules can bond together to form a solid. In chemistry, when we talk about a molecule, what we really mean is the smallest unit made of several atoms that can exhibit certain type of chemical property upon chemical reaction. For example, rock salt, NaCl. The molecular formula is 1 sodium and 1 chlorine. But in real rock salt, in solid form, we don't have just molecules made of one sodium and 1 chlorine, and then all these molecules just come together somehow to form this solid. Rather, each sodium atom is in fact in contact with neighboring chlorine atoms, and each chlorine atom is in contact with neighboring sodium atoms, and the bonding stretches on and on and on from sodium to chlorine to sodium to chlorine. It goes throughout the entire crystalline structure of rock salt. So in this sense, everything, all these atoms are tied together in the entire molecule through the extension of bonds. So we can say in this sense that the entire solid is really a giant molecule, so to speak. So therefore, we're not talking about bond within one atom, within one molecule, several atoms at most. We're talking about a bond throughout the entire piece of solid. So what's bonding these atoms together or molecules together to form a solid? There has to be enough force so that these molecules, these atoms do not fly apart, right? And the bonding mechanism in solids, when we study it, we should notice the similarity with the bonding mechanism within the molecule. The Coulomb force is still the key, and that is what binds different particles together is still the Coulomb attraction between positive and negative charges. Okay, and when it comes to bonding in solids, there are different types of solids: ionic, covalent, and metallic. The ionic covalent solids, really, what we do really, we just extend the ionic and covalent bonding between atoms in a molecule beyond the boundary of one molecule, we just keep on going throughout the entire solid, and we will get what's called an ionic solid or covalent solid, and we will see typical examples of that. Then the metallic solid, now that is something new. A metallic bond. We're going to study some more detail about metallic bond. So that will round up our study of molecular bonding, bonding in solids. So let's start with our first type, the ionic bond. So we have what's called ionic solids. These are solids formed by ionic bonds. And again, the example we use is rock salt, NaCl. Okay. In the previous lecture, we talked about how one sodium atom and one chlorine atom, when these get close together, there will be an electronic transfer from sodium to chlorine, forming a pair of ions. And then when they are at a certain distance, their energy is the lowest, lower than the case of a charged neutral sodium and a charged neutral chlorine, and therefore there is a bonding between them. But in the real solid NaCl crystal, we don't have just a bunch of NaCl molecules where only one sodium and one chlorine atom are tied together strongly, but there's not strong tie, not nearly as strong tie between different molecules of NaCl. That is not true. You can see here is an illustration of the crystal structure. The sodium atoms are these small red balls, and the chlorines are these larger blue balls. Each of these red balls, each of the sodium ion, is actually connected directly with 6 chlorine ions as its nearest neighbor. So the nearest neighbor are these 6 negative charged ions, oppositely charged. So there is certainly an attraction. The next nearest neighbor actually are other sodium atoms, like this guy, this guy, this guy, this guy, and so on. This, of course, is a repulsion, right? But the repulsion is less strong. It's not as strong as attraction because the distance between positive charges are less than the distance between positive and negative charge. So overall, you would have still an attractive force. And then you can go to the next neighbor and next neighbor, so on. And if we look at the situation for each chlorine, it's the same thing. It is actually being surrounded by 6 immediate neighbors. All of these are oppositely charged sodium, so the net force is attractive, and the next nearest neighbor would be neighboring chlorines, so that's a repulsive force, which is a little bit weaker than the attractive forces because of the distance again. So this structure extends throughout the entire crystal, forming a giant molecule. And there is a name in solid-state physics which we use to refer to this type of structure. It's called BCC, body-centered cubic. In a body-centered cubic, what we have here is a cube, and at the corner of each cube there is an ion, okay, and at the center of that cube there is also an ion of the same type. If you take a look at just the sodium or just the chlorine, you'll find that each of these two types of ions form it in itself. It forms a body-centered cubic structure. So we have a body-centered cubic structure for sodium, a body-centered cubic structure for chlorine, and these two structures interlock. They're interlocked to form this NaCl crystal structure. Now, what's causing these ions to stay together like this? Again, like I said before, it's because of Coulomb attraction. Okay, each ion is surrounded by 6 immediate neighbors that are oppositely charged, and then some next immediate neighbors that are negative, that are similarly charged. So there is going to be a net attraction, which corresponds to a lower electrical potential energy. And what we can do is to find, based on each ion, look at this ion as an example, okay? Using this ion as a reference, what is the total electrical potential energy due to the net attraction between this ion and its surrounding ions throughout the entire infinite large structure of this crystal? And what we get is what's called a Madelung constant, which varies from structure to structure depending on the geometry of the crystal structure. What is the Madelung structure? Madelung constant, how is it defined? Well, for NaCl, which is a BCC structure, here's what it looks like. Okay, again, I start from one particular ion. Say, I start from this sodium. Okay, start from this sodium, using this as the center of the coordinate system. And what I want to do is I want to add all the potential energies up between this guy and everybody else, starting from this as the center of the coordinate system. So let's see here. I go this way, this way, this way, this way, this way, this way. I will get what? I will get a negative potential energy, right? Because it's oppositely charged. And then if I go this way, this way, this way, this way, and so on, I will get positive potential energy and so on. So there are infinite number of terms. It start from here and extend in all directions to infinity. I will get infinite number of terms. Each term is of this form. Okay, Q1, Q2 divided by R12. Q1 is this charge. Q2 is the charge of the other ion. What is R12? R12 is the distance between the center of the coordinate system, which is this charge, and the other charge involved in the sum. Now, I can find this R, the distance between two charges, in vector form. In fact, let me write down the displacement vector between here and the set, which is the center of the coordinate system, and another ion. Now, all these ions are, if you look at the distance between this ion and the center in x, y, z direction, look at the x. Basically, look at x, y, z components of the position vector of any one of these ions. You find that they're all integer multiples of this length. This length is called r. It's called r from here to there. For example, this guy has, if you call this x direction, it's x equals 1r, y equals 0, and z equals 0, right? If you look at that guy, okay, and then you have x equals to 1 unit, y also equals to 1 unit, and z also equals to 1 unit, and so on. So in general, I can rewrite r of ijk which is the position vector of an ion whose location is given by this. It is r, which is the unit length between two neighboring ions, times I. I is here an integer, 1, 2, 3, 0, 1, 2, 3, 4, and so on. So it is this far away, I times r away from the x-axis, from the center of the x-axis. Okay, so in this case, for example, I would be equal to 1 if you call this the x-axis. So this is one step away in the x direction from the center. So therefore, I equals 1. Okay, and then also in the y direction, you go several steps up or several steps down. That will determine the constant j here. J is also an integer. R times j, for example, this guy would have j equal to positive 1. If you start here, this is the this guy would have j equal to 0 if this is the x-axis, but this one would have j equal to 1 if you call this the y-axis, right? And this guy would have j equal to negative 1 because you start with positive y direction going this way. So therefore, by counting all the possible integer values of I, j, k, you can find the position vector of any other ion in the entire crystal structure. So I, j, k are integers. They can be positive and negative. They can extend from negative infinity to positive infinity. Okay, what is the charge at the corner of this position vector? That is interesting because that actually alternates. You see, every neighbor, okay, if you start this at negative, all of its immediate neighbors are positive, which means, for example, going from here to there, you only change j by 1 unit, right? The y direction, right? You do not change x direction, nor do you change z direction. So you see, if I change any one of these numbers, I, j, k, by 1 unit, okay, what do I end up? I end up going from positive to negative or negative to positive. And therefore, this is how I would write Qijk, which is the charge at the corner of this particular position ijk. It's negative 1 to the power of I plus j plus k, absolute value. The negative positive makes no difference. It simply depends on whether you go this way or that way. That's positive, negative. And times E. E is the absolute value of the charge. So that's how you alternate. If you change I, j, k by 1 unit, leaving the other two the same, you're going to alternate between positive and negative charges. Okay, and so this is Q, which we plug in here as Q2. Q1 is just the charge at the center, which never changes, which we call positive E. So suppose we use sodium as a reference. Okay, and then R is given by this, given by the absolute value of this vector. Okay, the modulus of this vector. So you see here, K times E times the other charge, Qijk, divided by the modulus of, or the length of this vector, Rijk. This is the force, this is the potential due to the charge at the center and the charge at this particular location. I, j, and k needs to be summed up because we have to add all the three-dimensional contributions up. So it's a 3 sum. But I and j and k, they cannot be 0. They cannot be simultaneously 0 because then you go to the charge itself. You cannot do that. Okay, so you exclude the 0, 0, 0 term, but everything else, all the other possibilities, I, j, k, you need to sum it up. So it's a giant sum. Let me take the constant out. There's an e here, there's another e here. Take that out. Negative ke squared over r. Okay. And then you have this sum. I already took that r out. Took that r out, r out, r out. What's left is I squared plus j squared plus k squared. This is a threefold infinite sum. I, j, k. Going from negative to positive infinity, each of them, excluding the point 0, 0, 0. If you do that, then you get 0 plus 0 plus 0, you get 0. We do not count that. This sum is an alternating sum. Okay? Every term goes from positive to negative. You change only one of these three indices by 1. And that sum, unfortunately, is not very easy to evaluate. If you try to add from small values, say I equal to 0, I equal to 1, j equal to 0, and you try to start, basically what you do is you try to start from the immediate neighbors and the nearest immediate neighbor. You try to expand gradually out from the center. you find this sum, which we call alpha, this number, will change very slowly. Will change very slowly. It does not, in words, it does not converge. This infinite series does not converge rapidly. This is because you're dealing with 1 over r. You're not dealing with same like 1 over r squared or 1 over power to the 6, which will converge rapidly. Here you're only dealing with 1 over r. The Coulomb force is a long-ranged force. The force between this guy and this guy is strong, but the force even between this guy is also pretty strong. Even between this one is relatively strong, and so on. So it's a long-range force contributing to the slow convergence of this constant, which we call the Madelung constant. Okay. Fortunately, however, there are clever ways for us to calculate this approximately. We do not just simply start from the smallest value I, j, k and gradually expand. That will lead to too many terms that you need to keep in order to keep this alpha accurate. There are clever ways to approximate that, which I'm not going to talk about here, but it can be done. And alpha can be calculated to very high precision. Here is the value of alpha that I copied with so many sig figures. It's roughly equal to 1.75. That's all you need to know. That's the Madelung constant for BCC, with NaCl being an example. So you see, this Madelung constant really depends on how the ions are arranged, what kind of geometry it is. This is called the crystal structure. All right. Now, the Madelung constant leads to a term which is the attractive potential, negative attractive potential, Coulomb potential among all these ions in the entire crystal. Okay, in the entire crystal. You have to add contributions of everything in the crystal up because everybody attracts or repels with everybody else. You have to count them. It's not a single molecule anymore. But there is another term also we have to consider, and that term corresponds to repulsive force. So as the ions get closer and closer together, the attractive term, which we just talked about, keeps on going down, right? But as the ions get too close to each other, the force turns repulsive, and it's because the positive ions get too close to each other. The nucleus would get too close to each other. They start to repel each other significantly, and therefore the overall potential goes up. So you see the potential first goes down. That's because of this term, okay, the Coulomb attraction. And then start to go up. It's a function of r. What's r? R is again the distance between the two nearest neighbor ions. It's the distance between this guy and that guy, okay? That's r. And then so r, as r changes, U total first goes down and goes up. And clearly, there is an optimum point at r naught. There is an optimum point. At this optimum point, the total potential energy is the lowest. And this is what we go for. This is where the crystal will settle down. So it will form a lattice whose closest ion-to-ion separation is R naught, because that is where the energy is the lowest. How do you find that R naught and how do you find that U naught? Simple. All you need to know is what is U attractive. We already know that's the Madelung constant alpha right here. And the repulsive force, the repulsive potential is sharper than that. Okay, it's not 1 over r, it's actually 1 over r to the power m. M is greater than 1. Otherwise, it will not be able to compete with the negative potential. So it goes up like this, and you just set the derivative equal to 0 to find the minimum value, and this is what you get. If you set derivative equal to 0, that's what you find. Okay, this energy is called ionic cohesive energy. What does that mean? It means that when the crystal reaches equilibrium, the neighboring ions are separated by this much, by R naught, where the energy is the lowest. But if you pull these ions apart, okay, suppose you take all these ions, from the entire crystal and you separate them all to infinity, then R becomes infinity, right? You have to do work. How much work do you have to do? The work you have to do to separate each pair of ion is U naught, because you have to take the energy from this negative value to 0 when R equals infinity, right? So you have to give each pair of ions, each pair of NaCl ion, this much energy in order to break them apart. This is called ionic cohesive energy. The greater this energy, the more stable this structure is, because it's difficult to give it a lot of energy in order to break it apart. So this is ionic cohesive energy. Now, NaCl, or rock salt, is just a typical example of ionic crystal. There are many more ionic crystals, and they have something, they share some of the common properties. Because because of the fact that ionic crystals are pretty stable due to the large value of U naught. This is 7.84 eV. That's quite large. It usually form a pretty stable and strong solid. That's why the melting point is generally pretty high, a few hundred degrees. And it also has relatively high mechanical strength. It's not easy to break them. As far as electrical conductivity, however, they're all insulators, because all the ions, all the electrons are trapped inside these ions. They cannot simply hop from one ion to the next, or just get loose within the crystal. So therefore, these are all electrical insulators. And how does an ionic crystal respond to visible light and IR? What if you illuminate with visible light? Well, the table salt as a single crystal is transparent, right? That's not just for table salt. It is also true for all ionic crystals. They're all transparent to visible light. And that is because the bonding is very strong. And the electrons will take more than a couple of EVs of energy in order to make electronic transitions. Therefore, visible light, that simply because it does not have more than enough energy to excite the electrons within the ionic crystal, and therefore they will not be absorbed by the ions, and as a result they pass through. Visible light can pass through without loss of energy. Therefore, the crystal is transparent to visible light. On the other hand, the crystal will absorb infrared, even though infrared has lower energy than visible light photon. Why is that? It's because you cannot cause the electrons to make orbital jumps, but you have enough energy in IR to cause each ion to shake, to vibrate, okay? To vibrate. So we're talking about vibrational energy of the ion as a whole, not the electronic energy change within each ion. And that happens to be in the IR infrared range. So these guys can actually absorb infrared, even though they do not absorb visible light. So that's an overview of ionic crystal. But now let's take a look at covalent crystals. A covalent crystal is really made of large number of atoms that are tied together with covalent bond, not ionic bond. And the most striking example of covalent solid is the elemental form of carbon. I should say elemental forms of carbon.